positive. So when we take numbers from the literature, the spin diffusion length and the spin Hall angle that had been reported, we would expect an additional positive contribution. And so now we really start scratching our head and said, okay, I don't know, what is this negative thing? So then we thought, okay, let's do a control experiment. We thought, let's measure what happens in copper. Copper is a much lighter element than gold, and since it's lighter, spin orbit effects are much weaker, and so spin Hall effects should be much weaker. But what we see in copper is that if you look at the non-local resistance as a function of temperature, it behaves exactly the same way. It's positive at high temperatures, goes to 0 at about 90 Kelvin, and then is written here. So that was very puzzling because, I mean, we know the spin orbit coupling is much weaker than in gold, but the signal is still large. You know? We know that the spin diffusion length in copper is much longer, but if you look at how this signal changes as a function of distance between wires, it changes exactly the same way as it did in the gold. Namely, it's given by the geometry of the sample. And so, but what's similar between the two samples is that the mean free path is very similar. And so this told us that what we see is not due to spin transport. What happens is we have like a ballistic contribution to the charge transport that we have to account for. And so essentially what happens is the following. This slide is very busy, but so we know that as we pass a current through our device, diffusively some of the current gets into the second Hall bar region, and that's described by this expression here, by this exponential of the this distance over the width. And then we assume that some of the electrons that get here scatter ballistically into the wire, and this contribution actually is negative. And it goes as a function of the width over the mean free path. And if we use this simple expression, which is hand-wavingly described, we can actually fit all the data that we have. So these are all the non-local resistances plotted as a function of the mean free path, which we get from the resistivity for different distances and different temperatures. And it fits the data very well. And unfortunately, what it means is that we don't see any contribution of spin transport. And if we think that the spin signal is within the noise of our data here, then the spin Hall angle of gold is at best 2%. So much smaller than was predicted by this earlier group in Japan. So, but what do we do now? I mean, we set out to see if we can determine these spin Hall effects